Still raining outside?
Oh, yeah.
Yeah. But it's not cold. No, that's right. Okay.
Yeah, the bus took off in front of me and I got soaked. Yeah.
Okay. Very nice. It is 8 a.m. now, so let's start our lecture today. Today, we will complete our topic about routing algorithms. At first, welcome to our lecture. I hope that you enjoyed the assignment and you found the assignment useful and helpful for you to understand the topic of this day. Okay, so in this assignment, you were required to find the best way from the source to destination. Actually, we were required to find the way with the minimum cost to reach from the source to destination. And in fact, I was inspired by this problem by the movie of The Lord of the Rings. Anyone here watched this movie before? Yeah. So in this movie, the heroes were required to go from the Shire to Mordor to destroy the ring. And they have many ways to reach from the Shire, which is the source, to Mordor, which is the destination. And each way has its own specifications according to the safety. Okay, so the heroes were required to select the way which is more safer or has more safety than the other routes to the model, which means that routing protocols are not limited to routers only. Sometimes we need to use a routing protocol in our life. Okay, so this is for jumping with you. Let's start our topic today. As a quick revision, we know one of the responsibilities of routers is to make routing. We have many routes to reach from source to destination, and the route is a set of links where data moves through between the source and destination. And each source can take single path routing, one path for each session, or we may have multi-path routing, multi-paths for each session. And the advantage of taking multi-path routing is that we distribute our traffic over multiple paths. So no path is too loaded. Okay, so we don't want the path to be overloaded. So one of the advantages of taking multi-path to reach to the destination is to distribute your traffic at over many routes or many ways to reach to the destination. Okay, and another function from the router, after taking the routing decision, we must make forwarding. We must forward your packet to your destination. Okay, so once packet is received at the router will check the destination address to check where do you want to go. Okay, you want to go to this network, so I will look at my routing table. Okay, so I must forward your data through this interface to reach to this network. So it is like that we have the input ports of the router connect to the output ports to the router. Once we receive as a router, once the routers receive a packet at one of the input ports, it will forward the output. It will output your packet through one of the output ports. Okay, so how can routers make routing? We know that the routers exchange their routing tables. We want to know in this lecture how this routing table can be built, how the routers can take the decision of routing your packets to certain way or certain route. Okay, so let's represent our network topology in a graph. This graph consists of 1, 2, 3, 4. We have number of vertices. Each vertex represent router, and we have set of edges. Each edge represent a physical link that connect between node I to node J. So this is one edge, second edge, third edge, fourth edge, and the function of each edge is to connect between two nodes, between two routers in the network. Okay, each link must have cost value. This cost value must describe to me the properties of this link in order to be able to take a decision to select this link on my way or not select this link to my way. So the cost, for example, this C from 1 to 3. The cost from node 1 to node 3 maybe represent the speed of the link, maybe represent the delay of this link, maybe represent the safety or security on this link, can represent the congestion on this link. So we represent all of these parameters in one term called cost. And based on the routing protocols that you are going to use, this cost, we will represent it again to certain metric. For example, we have routing protocols called RIP, Routing Information Protocol. In RIP, the metric or the cost is calculated as minimizing the number of hops. We want to minimize the number of routers that our packets will move through to reach to the destination. So the cost here of this link means that number of hops. Okay. In another protocol, commercial protocol called OSPF, okay, protocol, the metric is the speed of the link. So the cost here is equal to the speed of the link. And third one called EIGRB protocol. The metric is the delay. You are not required to know these protocols, okay? They are the commercial protocols used in the market, okay? And during this course, I think you are not required to know them, okay? You only required to know that we have REP, routing information protocol. The metric is the number of hops. OSPF, open short path first, okay, yeah. The metric is the speed of the link, okay. In ENGR, the metric is the delay plus number of hops, okay. And all of these protocols are used to enable routers under the same network administration to communicate with each other. So this, what I explain now is not required from you during this course, but this is for your knowledge. Okay. If we return back to the last slide in our previous lecture, we have summary of the commercial routing protocols. Okay. And we have two types of routing protocols. Okay. These routing protocols, which we can see there view. Yeah, these ones. Okay, so we have interior gateway protocols and exterior gateway protocols. And interior gateway protocols, they are the protocols that used to enable routers inside the same network administrations to communicate with each other. For example, the routers inside Rogers internet service provider are communicating using one of the interior gateway protocols. Routers inside TELUS, okay, are communicating using one of the routers of interior gateway protocols, okay. But if the routers in Rogers want to communicate with the routers in TELUS, they must use exterior gateway protocol. This is clear for you, okay? So we classify the interior gateway protocols into two categories. The first one is distance vector routing protocol. Distance vector routing protocol, the metric in these protocols depend on the number of hops to minimize the number of hops to reach to the destination. Okay, we have REP, routing information protocol, and IGRB protocol, which we make improvement over it to be EIGRB. In EIGRB, it is advanced routing protocol version over the REP, over the routing information protocol. So in EIGRB, the metric is the delay plus the number of hops. Okay, and link state routing protocols, from its name, if you can see here, distance vector, so the metric is the distance, number of hops. Link state is the state of the link, the speed of the link. Okay, so it's like the OSPF and ISIS. The OSPF is currently the most popular routing protocol used in the internet service provider. Okay, so if you have an interview to work in data routing, okay, so you must be, your background must be solid in this protocol, OSPF. Okay, but OSPF, from my opinion, is the best one to use as a routing protocol, but it has many disadvantages, such as it requires huge processing, huge RAM, huge CPU. So not all routers can deal with the OSPF. Only the high resources routers that can use OSPF. So OSPF protocols are used at the routers at the internet service providers, okay, as they have the resources and have the capabilities to buy huge routers that can have huge resources such as RAM, CPU. Okay, so this is as summary of what is the meaning of cost. Okay, so the meaning of cost depend on the used routing protocol in your network. So the cost of the RIB is different from the cost from OSPF, for example. The RIB is that to minimize the number of hops. For OSPF, we want to select the way with the highest speed, for example. Okay, so returning back to this. Okay, so our routing problem is called that routing. We need to select the shortest path problem, or shortest path here means minimum cost. We want to select the path to the destination with minimum cost. And again, what is the meaning of cost? It depends on the routing protocol. So as I told you, remember this, the cost here depend on the used routing protocol. So in general, we will say cost. We want to find the way from source to destination with minimum cost. Okay, so this problem can be solved using two algorithms. The first one is called Bellman-Ford algorithm. The second one is called Dijkstra algorithm. Today, we want to discuss or to understand more the Bellman-Ford algorithm. I know that you had a previous example on it on your assignment, but in case of your understanding for this algorithm is not 100%, we want to reach to this percentage during this lecture. Okay, so the Bellman-Ford algorithm is one of the simplest algorithms used in routing algorithms. This algorithm is applied by the router. So what I do as network administrator is to go to the router and just install the algorithm. For example, in the router, I will write in the configuration of the router RIB version 1 or version 2. So I select the protocol and what is its version. So I activated the routing information protocol on the router. So the router now know how to communicate. So the administrator only activates the name of the your routing algorithm, and all the routing algorithms files are pre-installed on the router. They only need to be activated. Okay, so once you write this command in the router, so the router, okay, you need me to activate the routing information protocol file. So I will activate it. Okay, in the routing information protocol file, there is an algorithm that the router will use. Okay, one of these algorithms is Bellman-Ford algorithm. Okay, we want today to understand how routers deal, how the routers communicate, how the algorithms deployed by the routers can be executed. Okay, so this is the main objective of this lecture. So we want to explain the Bellman-Ford algorithm. The Bellman-Ford algorithm, as I told you, is the simplest routing algorithm. It enables us to find the shortest path to the destination, or the minimum cost path, or minimum cost way to the destination. Its idea is based on that in order to make the source reach to the destination, we must to go via the neighbors of the source. Okay, so it is used in cases that where the source is not directly connected to the destinations most of times. But some cases we have the source is connected to the destination, but we can also use the Bellman-Ford. Okay, but the main idea of the Bellman-Ford is to enable routers that are far away from some destinations to reach to these destinations through the neighbors of the source. Okay, so we have here an example. We have here a network. Okay, this is 1, 2, 3, 4, and we can make it more longer. Four, 5, then it's source and this is destination. Okay, so this is our network, and we want to go from the source to destination. From this figure, you have 2 ways to reach to the destination. Okay, can anyone tell me the first one? So I will go to from S to 4 and D. Okay, and the second one is S3, 5 and D. Correct? Okay, so if I want to tell you, I want to know the cost of each way. How can we calculate it?
You'd sum the costs along that path.
So you will tell me that we will sum the cost along this path. This is correct. So here I will add the cost from the source to node 2, so plus the base cost from node 2 to destination. This is correct? Where the base cost from node 2 to the destination is the cost from along the remaining links to the way to the destination. This is correct. Also, I can write it as the cost from source to node 3 plus the base from node 3 to destination. So your optimization problem here is to minimize this function or this function. Okay, we want to minimize the cost from source to destination. So we want to select the best with minimum summations of the costs of over the link. So this is our optimization problem that we want to solve. And one way to solve this problem is to use Bellman-Ford algorithm. In Bellman-Ford algorithm, the cost of the path is represented by this notion. So if I write here B of I of j and T is the number of iteration, which means that the cost from node I to node j. And if node I and node j are not connected, so this value must equal to infinity. Okay, and if node I is the node j, it is the same node. If I want to go from node S and reach to node S, so I will not move, so the cost will be equal 0. This is clear for you? So if I can't reach to the destination through direct link, So the cost will be infinity. And if I want to reach to myself, there is no cost. Okay, so the cost will be 0. In order to understand the Bellman-Ford algorithm, let's take this and discuss together the solution of this example. So here we have this node 1 and this is node. This is fine. Okay. And we have 1, 2, 4, 1, 3, 1. Okay, and we want to find the best way to reach from the source to destination. Okay, so the first step, you will make this table. 1, 2, 3, 4, 5, 6. And here number of iteration. And we will start by iteration number 0. Okay, at first, the first iteration, you are now at your node. Okay, so when you are at node 1, can you reach to node 6, which is your destination, without any movement? So we will write the cost as infinity. Okay, and in this table, we want also to write the next hop. Okay, so in this case, we will not move. Okay, so we will assume that if we will not move, the next hop will be -1. Okay, so here you are at node 1, you will not move. Okay, so your next hop will be -1. Okay, this is -1. Okay, and node 2, you are now at node 2. Can you reach to your destination without any movement? So the cost will be infinity. Okay, and your next hop will be -1, as there is no next hop. Okay, at node 3, can you reach? No. Node 4 is the same case. Yes. Node 5 is the name, it's the same case. Node 6, which is the destination, what is the cost? 0. Okay, and your next hop will be is the node 6 itself. I want to reach to node 6, and I am already at node 6, so my next destination is the same node, which is the node. Okay, so this is one of the steps to solve the Bellman-Ford algorithm. The first iteration, the cost of all nodes will be infinity, as in order to reach to the destination, I must go, I must move. So without any movement, I will not be able to reach to the destination. So the cost of the path will be infinity. Okay, the second iteration. We want node 1 to reach to the destination. Okay, so node 1 will start to move. Okay, in the second iteration. The node 1 can reach to the destination through node 2 or node 3. This is correct? Okay, so we will find the minimum between, if I go through node 2 and if I go through node 3. If I go to node 2, the cost of this link is 1. And I will add it to the path cost from node 2 in the previous iteration. So I will add 1 to infinity. Okay, this is the cost of the first way to from node I to the destination. Okay, another way is to go through from node 1 to node 3 in order to reach to the destination. The cost of this link is 2, and I will add it to the cost of the path from node 3 to destination, which will equal to infinity. Okay, so here the result of this value, means infinity, this means infinity, so the result will be infinity. And I will put my destination as it is infinity as -1. For node 2, okay, I can reach to the destination through node 4 or through node 5. Okay, so and this is 3. Okay, so I will calculate the minimum between the cost from 2 to 4 is 3 plus the cost from the path through the node 4, which is infinity. Okay, and I will compare it to going from node 2 to node 5, which is 4, and I will add it to the path cost from node 5 to destination, which will be infinity. So infinity and this infinity, the minimum between infinity and infinity will be infinity. So I will put the next destination will be -1. Okay, node number 3. Can anyone tell me the minimum between what?
So it'd be the cost of getting from 3 to 6 and then 6 to itself, so 3 plus 0. Oh, no, sorry, I was looking at node 4.
No, not 3. 3
Uh,
this is 5. Okay.
So 1, like 3 to 4 would be 1 plus infinity.
It
or
will
3 to
be,
5.
sorry, 1, which is the cost from node 3 to node 4, plus the path cost from node 4 to destination, which is infinity. And I will compare it to 3, 5. Okay, so it will be 5 plus infinity. So the result will be infinity, and I will reach to it. The next destination will be -1.
You
For-
should explain why it's like the -1 part. I don't know.
Actually, it is a value that means that we still not have next destination. Okay, But once you have next destination, we will put the number of the node of the next node that you will use to reach to the destination, as you will reach, as you will see now in this example. Okay, node 4. Anyone help me else? Okay, so but explain why 3 plus 0. Okay.
3 is the cost from 4 to 6.
Okay,
And
so at first, how many ways to
then
reach?
one
It
path.
is only one. Yeah, so I must use this way. Is this correct? Yeah. So I don't have here minimum. Okay, I will add 3 plus
0.
y 0.
The cost from 6 to 7.
Okay, so I will use this way from 4 to your destination. Okay, so the cost of this link is 3 plus the path cost from 6 to itself, which is 0. So it is 3 plus 0. So the result will be 3. And what is your next destination here? What is your next destination?
Yeah,
What?
are you there? Like,
Yeah, here we wrote -1 as there is no destination.
also 6.
This is your destination. So the cost to reach to this, my destination is 3. And in order to reach to this destination, my next node will be node 6, which is the destination. Okay. Node 5. Anyone else? Man, can you tell me how to reach to the destination from node 5?
Cost is
1. How many ways at first?
only one
Only one way. So 1 plus
is
0. So I will go through this link to the destination. So the cost of this link between 5 and 6 is 1 plus the cost of path 6 to reach the destination, which is 0. So it is 1 plus 0. It will equal 1. And your next destination will be okay. And for node 6, which is a destination, it will be its value will be 0, and next destination will be 6 at all iterations. Okay, as we are at the destination. Return me back to the second iteration. Okay. For node 1 to reach to the destination, how many ways again? 2. Okay. So this is, you answer me. Okay. So we have 2 ways. How we can calculate the cost of these 2 ways? So we want to find the minimum between what?
The cost from node 1 to 2, node 1 to 3.
Okay. So what should I write here?
1 plus the cost from.
What is 1? What is the 1? This one.
1 is the distance between node 1 and node 2.
So we are now calculating the cost
Between node 1 and 2.
to reach to the destination through node 2. Okay, so 1 is the cost from 1 to 2 plus.
Cost from 2 to destination.
Okay, what is the cost from 2 to the destination? Infinite. Okay, so we use the cost from the previous iteration. Okay, so it's infinite. Okay, and for the second path to the destination,
2 plus infinity.
2, which is the cost from 1 to 3 plus infinity. So the result will be infinity. Yeah. And your next destination is -1. Okay. For node 2, Duncan, can you help us?
For node 2,
Yeah, this is the fifth.
So that is going to be, there's still only one path. So we're just doing the minimum from 1 to 2, which is just going to be a cost of 1.
Here,
Yeah, or to go from 1 to 2.
no,
Starting.
Oh, starting at 2. Okay, so
Yeah.
the minimum, so you've got the path 2, 4, 6, which is a cost of, oh wait, do we have that many number of paths? Yeah. So, yeah, so we have the minimum of 2 to 4 to 6, which is 6, and then the minimum of 2, 5, 6, which is 5. So then that would give us a hop through 5 at a cost of 5.
okay, so can you explain it more to us? So we have two ways to reach to the destination.
Yes,
The first way is through
it's through 4.
network 4.
Yeah.
So I must compare between the minimum between through 4 and the minimum through 5.
Yeah.
Yeah. Okay. So through 4, what should I write?
So from 2, if we're going 2 to 4,
Okay.
it's a cost of 3.
Okay. So I must at first write the cost from 2 to 4.
Yeah.
Okay. Plus.
The cost of 4 to 6, which is also 3.
Okay, plus the cost of 4 to reach to the
Yeah.
destination, which is 3. Okay. And I must compare this way with
The other path, through
Yeah.
2 to 5 to 6.
so 2 to 5. Okay.
Yeah, 2 to 5 is 4.
Is 4
And then from 5 to 6 is 1.
is 1. Okay. So we have here 6 and 5. So the cost will be
5.
I will take the minimum, will be 5. And what is your next
Next hop would be 5 as well.
5? Okay, so in the second iteration, for node 2 to reach to the destination, the cost from the source from node 2 to the destination is 5. And we can reach to the destination through node number 5. Okay, this is clear for you? Okay, it's your turn now. Please help me to find the cost of node number 3.
So the iteration around, I moved ahead a little bit. Number 2?
Yeah,
That one there would be the minimum of.
we are here. Okay, how we can reach to the destination?
So the 2 paths you take are through 3 to 4.
3 to
Which
4.
would be 1 plus the previous version of 4, which is 3. And then the other option.
Yeah, 1 plus 3. Okay,
Yes. The other option is if you're going to node 5, so that would be
3
5
to 5. Okay,
plus the previous cost of 5, which is 1. So then your minimum would be to go through path 4, which is
so sorry, from 3 to 5, which is 5
5 plus 1.
plus 1. Okay,
Yeah. 1 is the cost of the last iteration of 5.
yes. Okay, so the result will be 4. Okay, so it will be 4
4.
through
4.
4. Okay. For node 4,
Sorry.
I want to calculate the value of node 4.
Yeah.
No change. Okay, so it will be 3 to node 6. And for node 5 will be also no change. It will be 1 through node. And okay, we'll have now the third iteration. Okay. Your turn.
To be honest, this is where I get stuck in the assignment, so.
So can you help me?
Sure.
Okay.
So for the first node, it's gonna go 1 to 2 and 1 to 3 again.
1, 2. Okay, so we want to find the minimum between these two paths. Okay, so the minimum between what?
So 1 to 2 is gonna be 1 again, which is your,
1 plus.
and then the last value 2, 2, 5.
Okay. And the second path.
And 1 to 3 is gonna be 2 for the travel, and then 3 is gonna be the last value of the.
3
pass forward.
So they are equal. Okay, so the cost would be 6 through node 2 or 6 through node 3. What should I do in this case? You don't have any idea?
See
This is a good solution. But what if after you make another iteration, you have convergence, but at the end you have two answers? What should you do? If you are a router and you have two paths to a destination with the same cost, what should you do?
I'd split the data equally between the two.
I would just pick.
Yeah, the simplest option would be to just choose the route through 2, because if you are implementing it in an algorithm, you compare if the cost through, say, node 3 is less than node 2, which it's not, so I just fall back to 2.
Okay.
Different ways of implementing.
I was gonna say pick the one with the least number of pops, but they have the same number.
Yeah, they have minimum cost, the same cost, the same cost. Okay, so ideally in the network, in this case, they use something called load balancing. So we split our traffic between the two nodes. Okay, so yeah, so we transmit one packet through this way, and the second packet through this way. One packet here, one packet here, one packet here, one packet here. Okay, as they are the same. Okay, so for node 2, okay, we finished. Turn it back to Aman.
2 paths. So
Okay.
do we do 4 and 6? The cost is 6 and then 5 is 5.
So I think it will be the same. Okay. And for node 3 also will be the same. And also this. And also this. We will make another iteration for we will receive the same results. The conversions will happen. So now, based on the Bellman-Ford algorithm, we can know that node 1 can reach to the destination with cost 6, which is the minimum cost, through 2 nodes, 2 or 3. Node 2 can reach to the destination, okay, with cost 5, and its next destination will be node 5, and node 3 can reach to the destination with cost 4 through node 4, and node 4 can reach to the destination with cost 3. The next destination will be node 6, and node 5 can reach to the destination through node 1 with cost 1, and next destination will node 6. So now we have our routing table, the cost of each path, and what is my next destination to reach to the to reach to my final destination. Okay.
So just to be clear, we always stop once the next iteration has no change from the previous
Yes. Yes. This is what we call convergence. Okay. So there is no change. So we must stop. Okay. Okay. So this is a summary for the Bellman-Ford algorithm. We want to minimize this function, the cost between node I and node J, plus the path cost from node J to the destination. Okay, and as you can see here, that and each node needs to know the cost of the outgoing edges to its neighbors. We need to know the cost of this link. We need to know the cost of this link in order to be able to calculate the best path to the destination, to calculate my routing table. So what we need here is to use message passing protocol. This is the protocol used between routers to exchange. Okay, so I have here, I'm connected with this link, and the cost of this link is certain number. I'm connected to this link, and the cost of this link is this certain number. So this is the message passing protocol. Each router will send its node ID. I am router 1, destination ID. I can reach to node 2, okay, with cost of minimum bus, the cost between the node 1 and node 2, okay, and I can reach to node 2 through which node. For example, here node 2, node ID node 2, destination ID will be node 6 with our final destination. Cost of the minimum bus I can reach from node 2 to node 6 with cost 5. Next node will be node 5. Okay, this is the content of the message sent from node 2 to node 1. Okay, node 1, I can reach to destination 6 with minimum cost 5 through node 5. Okay, so all the routers exchange these informations until we have convergence. Okay, until your routing table, the content of your routing table will be the same content of a man routing table, will be the same content of my routing table. Okay, in the next lecture, or you can solve this example at your home, okay, and try to form your routing table for each router. Okay, try to do it, and you have any question, feel free to ask me. My office hour will be tomorrow from 12 to 2 at EME for 263 office, EME, 12 to 2 p.m. tomorrow. Okay, so today we finished the Bellman-Ford algorithm. In the next lecture, we will discuss the Dijkstra algorithm and understand what is the difference between Bellman-Ford and Dijkstra. Okay, thank you everyone. Everything is clear to you till now? Okay. Today we will have our press lab finally. Yeah, okay. If you didn't upload your pre-lab through the campus, please upload it. Okay. Yeah.
Should have won. Really?